Okay, today we're going to ask the following question. Let's say we have two random variables, x and y, and say we know the distribution of x and y. Now let's add x and y to get the random variable z. What is the distribution of z? More generally, given n random variables with known distributions, how do we get the distribution of their sum exactly? Now you might say, wait a second, we've already kind of dealt with this, right? Remember, we did the law of large numbers, we did a lot of stuff with sums, but remember, in the law of large numbers, we took a limit. Something was true only in the limit as n goes to infinity. Here, we're thinking about a finite n, not necessarily a limit. Let's recall the case of the Bernoulli trials, where we do n independent trials, each of which has a probability p of success. We showed before that the number of successes is a random variable that has distribution given by the binomial distribution. So here's an idea. Let's write down the function f of t, which is pt plus 1 minus p. We can certainly do that. And if we compute the nth power of f of t, we get a large polynomial, but notice the coefficients of that polynomial are the probabilities of the binomial distribution. If we can summarize what we just said, if we let xi be the random variables that are 1 with probability p and 0 with probability 1 minus p, let x be the sum of those. If we define f of t to be the polynomial probability x equals 1 times t plus probability x equals 0, then when we take a high power of that polynomial, we get a big polynomial whose coefficients are the coefficients of the binomial distribution. So somehow, adding random variables is related to multiplying polynomials. Let's explore this. Now we make a definition. Let x be a random variable, then the probability generating function of x, called the PGF, is the function given by the expected value of t raised to the power of x. In particular, if x takes values in the natural numbers and or 0, then we could write g of x as a power series. The sum k equals 0 to infinity, t to the k times the probability x equals k. If x takes only finitely many values, then this is actually a polynomial. PGF has several properties, which we list here and we prove. We now state and prove a theorem. If x and y are independent variables, then the PGF of their sum is the product of their PGFs. Here's the proof. We can generalize this by induction. If we have a sequence of independent random variables, then the PGF of their sum is the product of their PGFs. Here's an alternative proof of the theorem that's valid when we can write the PGF as a power series, specifically when the random variables take values in the natural numbers or 0. Let's rework the example of Bernoulli trials and show that our result matches the statement of the theorem. Okay, here's an example. Let's say we roll 10 dice and add the values. Call this sum the random variable x. We showed earlier that the expected value of x is 35, simply because it's 10 times 7 halves. Here's a question though. What's the probability that x equals 35 exactly? Well, notice, without too much work, we can write down the PGF for any one of these random variables. Remember that it takes the values 1 through 6, each with probability 1/6. Therefore, that's a polynomial with powers 1 through 6 and coefficients 1/6, which we can factor as below. And therefore, the PGF of the sum is just the 10th power of that polynomial. Now, this is going to be very hard to compute by hand, but we can use computer algebra. For example, a system like Wolfram Alpha, we can go in here and just ask the computer, what is this polynomial raised to a high power? The computer tells us, for example, that the coefficient of t to the 35 in this polynomial is actually exactly 4,395,456. Therefore, the probability that x equals 35 is that 4 million ... number divided by 6 to the 10th, which is about 7.26%. Okay, remember this game we talked about a long time ago. We're going to flip coins, keep flipping until we get the first heads, and then stop. Let t be the random variable, which is the number of flips that we do. Remember we showed before, the probability that t equals k is 2 to the minus k, right? For example, the probability that it's equal to 1 is 1/2, because that means flipping ahead on the first trial. The probability that it's 2 is exactly the probability of the sequence th, etc. Let's write out the PGF of this function. We know all these probabilities, so we know the coefficient of this power series. And then using some tricks from geometric series, we can get a nice closed form formula for the probability generating function, which is t over 2 minus t. So for example, this function, its coefficients recover the probabilities, or conversely, the probabilities give us this function. Now, as such, it's not super useful because we already have a formula for the probabilities. But now let's ask a harder question. Let's say we modify the game. We're going to flip coins until we've gotten 3 heads total. Call the number of flips in that case x. And we could ask, here's a simple question. What's the probability that x equals 5? So specifically, what's the probability that when we get exactly 3 heads by the 5th flip? We can see that we can write x as the sum of 3 random variables, each of which have a known distribution. The reason is because think of playing this game where we flip until we get a head, and then stop, and then restart. And we do that 3 times. So we can write x equals t1 plus t2 plus t3, where each of the ti's have the distribution of flip until the first head. We know the PGF of those functions, we just computed it. Therefore, the PGF of x is the cube of those functions. In this case, it's t cubed over 2 minus t cubed. So we're asking the question, what is the coefficient of t to the 5th in that function? Of course, notice since there's a factor of t to the 3 there, that's exactly the same as the coefficient of t squared in the function 1 over 2 minus t cubed. Well, how do we get that? Turns out we could use Taylor series. Let's compute the first 2 derivatives of this function, as we see here. And remember, in a power series, the coefficient of t squared is the second derivative of the function, evaluated at 0, divided by 2. In this case, we look at the second derivative, we plug in 0, we divide by 2, and we get 3/16. And that's the answer. And I think this is a good place to stop.